Welcome everyone. This lecture is about the source entropy. This is a brief outline of the lecture. First, we define the source entropy. Then we study the entropy of the binary source. And finally, we prove the important property that the entropy is non-negative and falls between 0 and log base 2 of m, where m is the number of symbols in the source alphabet. We start, as we have started also in previous lectures, with our model of a discrete time information source. The source under consideration is a discrete time source. The number of symbols in the source is finite and countable. The source is discrete in time in the sense that it produces one symbol out of the m possible symbols every time unit. The output of the source in the first time slot is a random variable x1. The output in the second time slot is another random variable x2, and so on. Over the source, we define a probability distribution P of S equal S sub m equal P sub m. That is, there is an associated probability for each symbol Si produced by the source. S1 is produced with probability P1, S2 is produced with probability P2, and S sub m is produced with probability P sub m. In a previous lecture, we defined the information content of each symbol in the alphabet using this relationship I of S sub m equal log base 2 1 over P sub m in bits. Using this definition of information, we can say that the information content of symbol S1 is log base 2 1 over P1, that of S2 is log base 2 1 over P2, and that of S sub m is log base 2 1 over P sub m. So these are the individual information produced by each one of the symbols Si. Now we define the average information per source symbol. Symbol S1 occurs with probability P1 and carries an amount of information log base 2 1 over P1. Symbol S2 occurs with probability P2 and carries an amount of information log base 2 1 over P2, and so on. From this we conclude that the information content of each symbol is a random variable, and this is the associated probability with this random variable. This random variable is a discrete one, and therefore we can compute the expected value or the average amount of information of this random variable as a product of the probability of occurrence times the amount of information for each symbol. This is expressed mathematically as the expected value of the random variable. This is also called the entropy of the source, and it equals the product of Pi times log base 2 1 over Pi, and the summation is carried out over all symbols in the source. So the entropy of the source is given by this formula, Pi log base 2 1 over Pi, and the units are in bits per symbol. We have two interpretations for the entropy. The first, entropy is a measure of the information content in the source. As we can see from here, it's the expected value of the amount of information in the source, and also it's a measure of the uncertainty in the source, since information is related to the uncertainty in the source through this relationship 1 over pi. As the probability decreases, the uncertainty increases and the amount of information increases. So these two properties, or these two interpretations, are related closely with this definition of the information for each symbol. Symbols with higher probability have less uncertainty. Symbols with small probabilities have higher amount of uncertainty. That is, they carry larger amount of information. In the special case, when the symbols in the source are equally likely, the entropy is given as 1 over m log base 2 of m, and this equals log base 2 of m. Now we consider the binary source. Consider a random binary source S with probability assignment over its symbols as probability that S equals 1 equal P, probability that S equals to 0 is 1 minus P. The entropy of the source is H of P equal minus P, which is the probability of 1, log base 2 P minus the probability of a 0, which is 1 minus P, log base 2 1 minus P in bits per symbol. In this figure, we plot the entropy function H of P as a function of P, which is the probability of 1. We see that when P equal to 0, the entropy is 0. When P is 1, the entropy is 0. And when P equals 1/2, the entropy is maximum. We also notice that the entropy function is concave upward and attains its maximum value when the symbols are equally probable. When P equal to 0, this means that symbol 1 occurs with probability 0. In this case, 0 occurs with probability 1. At this end, one of the symbols occurs with probability 1, and therefore the source entropy is 0. When P equals 1, also this symbol occurs with probability 1, and therefore the entropy is 0. H of P equals to 0 at P equals to 0 and at P equal 1, and this is emphasized by the fact that one of the symbols occurs with probability 1. And when one of the symbols occurs with probability 1, this means that there is no uncertainty in the source, which means that the entropy of the source is 0. H of P is maximum, which equals to 1. This is the maximum value when P equals 1/2, that is, symbols are equally probable. This means that when P is 1/2, the source has maximum amount of uncertainty. Now we prove this lemma for an M-array information source. The entropy H of S is non-negative and falls between 0 and log base 2 of M. M is the number of symbols in the source alphabet. The minimum value of the source which is 0, occurs when one of the symbols occurs with probability 1 and the rest with probability 0. The maximum value is attained when symbols are equally probable, and the maximum value is given by log base 2 of m. We can easily prove that the minimum value of the entropy equals to 0, and this is attained when one of the symbols occurs with probability 1. In this case, we can make use of this limit as p equals to 0 of p log p, which also equals limit as p approaches 1 of p log p, and this is equals to 0. As we know, the entropy of the source is given as minus summation of pi log base 2 of pi. When one of the symbols is 1, so we have 1 log base 2 of 1 equal to 0 for one symbol, and for the rest of the symbols we have 0 log base 2 of 0, which is also equals to 0. Next, we show that the entropy is maximum when source probabilities are equal. That is, when pi equal 1 over m. Actually, we will prove this in 2 steps. But before doing that, we introduce what is called the relative entropy d of x and y. This is a distance measure between the distribution x and the distribution y. The divergence or distance between distribution x and distribution y, it's defined as d of x and y, the distance or the divergence between distribution x and distribution y equals summation from j equal 1 to m p sub j log p sub j over q sub j. P sub j is the distribution under consideration for the random variable x. Q sub j is a reference distribution with probabilities q1, q2 up to q sub m. Of course, x is a random variable with the distributions p sub j. This is our given probability mass function. Y is a reference random variable with distribution q sub j. First, we prove that the divergence d between distributions x and y is non-negative, larger than or equal to 0. We can rewrite this divergence as d of x and y equal summation p sub j log p sub j over q sub j. We can reverse the order for q sub j and p sub j, which equals minus p sub j log q sub j. Now q sub j comes into the numerator, q sub j divided by p sub j, or minus, we take the minus sign to the opposite side, minus d of x and y equal summation p sub j log q sub j divided by p sub j. We also know this fact about the logarithmic function, that log x is always less than or equal to x minus 1. This is the curve y equal ln x, y equal log x, and this curve always falls below this straight line y equal x minus 1. This means that this summation p sub j log q sub j over p sub j, we can replace this logarithmic term with this quantity, which is qj divided by p sub j minus 1. So this quantity is smaller than or equal to this straight line. Now we can simplify this term as less than or equal to q sub j. This term cancels out with this term, so we are left with q sub j minus p sub j minus p sub j, and we also know that the summation of all probabilities equals to 1, so this summation is 1. This summation is also 1, which means that d of x and y is greater than, we can reverse this inequality, and therefore we have d of x and y greater than or equal to 0. Therefore, the relative entropy or the divergence between x and y is a non-negative quantity. Of course, when these probabilities are equal, that is when q sub j equal p sub j, this ratio is 1, and so log 1 equal to 0. This means that the relative entropy between distribution x and distribution y is 0 only when p1 equals q1, p2 equals q2, p sub m equals q sub m. In this case, the distance or the relative entropy equals to 0. Otherwise, the divergence is non-negative. It's always greater than or equal to 0. So this is the first part in proving that lemma, that the divergence d between distributions x and y is non-negative. Now we come to the second step. Now we let y be a uniform distribution. In this case, we have assumed that the reference distribution is a uniform. So let y be a uniform distribution. In this case, the probability for any symbol in this distribution is 1 over m. We compute the relative entropy between our distribution x and this reference distribution as d of x and y equals summation p sub j log p sub j over q sub j. We can expand this summation as p sub j log p sub j minus p sub j log q sub j. We can easily recognize that the first summation is nothing but the negative of the entropy of the source x. So this is minus h of x. As for the second term, we have p sub j log q sub j equal 1 over m, since the symbols in the reference distribution are equally probable. So this is p sub j log 1 over m, which equals minus h of x minus, this is a constant, we can take it out, of the summation minus log 1 over m, and we are left with the summation of P sub j. But again, the summation over all probabilities of this distribution P sub j equals 1. Therefore, d of x and y equals minus h of x plus log base 2 of m. Therefore, d equals log m minus h of x, and we also know the relative entropy d is greater than or equal to 0. Therefore, we conclude that h of x is less than or equal to log base 2 of m. So h of x is less than or equal log base 2 of m. We also notice that when P sub j equal Q sub j, when P sub j equal Q sub j, the value of this logarithm is 0. Therefore, d equal to 0, and in this case, h of x equals log base 2 of m. Otherwise, h of x is less than or equal to log base 2 of m. To conclude, the entropy of a source is a non-negative quantity which falls between 0 and log base 2 of m. The minimum value is attained when one of the symbols assumes a probability of 1 and the rest are zeros. The maximum value of the entropy is attained when all symbols are equally likely. This concludes this lecture.